Okay, I'm going to talk today about how to incorporate auxiliary information into your model using Bayesian methods. So I want to start with a question. How many times have you fit a model and then checked to see if the parameter estimates made sense? Maybe if that slope coefficient is 10, sure, fine, that could happen. But 100 or 1,000,000, something went wrong. Maybe I need to fit a different model, or maybe the optimizer got messed up. So that tells you something. You know something that your analysis is not taking into account, and so that's an opportunity you can improve it. So that's the pitch for Bayesian methods, taking into account this additional information that's not explicitly in your model through the prior distribution. But admittedly, this is not easy. Sometimes we like to think it is, or at least explain it as if it is, but this is a very difficult problem translating this information. So my solution is going to be essentially think real hard about the problem. But I'm going to guide you in thinking about this problem using a conceptual framework, hopefully making it a lot easier. So from here, the game plan is to start with the Bayesian story. In other words, what we tell ourselves we're doing when we do Bayesian statistics. From there, we'll use that to frame how to think about the prior, which will then help us think about how to select the prior. And we'll have an example. But of course, see the paper for more detail and more examples. So the Bayesian story. This starts with a philosophical argument trying to conclude that uncertainty is subject to the laws of probability. And there are several different arguments that potentially get you there. But the point is, you really start with this to get Bayesian inference to fall out. If uncertainty is subject to the laws of probability, probability represents degrees of belief, then you can use the laws of probability to constrain how your degrees of belief must behave. In particular, using Bayes' rule, a theorem of probability, you get a consistent inferential framework that tells you how to update your beliefs about whatever, about reality, in response to new information. And this is great. It makes philosophers very happy, for example. The problem, of course, is a very common criticism of Bayesian statistics is that in practice, whenever you use it, this prior seems made up. Kind of just pull it from somewhere. What is it? Well, there is a glib Bayesian response to this. Best represented by redacted Darth Vader here. Apparently Disney would not give us the rights to use his image. I guess they don't care about Bayesian statistics very much. You know what? Sucks for them, I guess. But in any case, the glib response is that the prior comes from the same place as the likelihood. They're both made up. And that's true, I think, but it's not necessarily a helpful response because you still have to choose the prior at the end of the day. So how do you do that? So I'm going to try to help you do that. We have to operationalize this. We don't come preformed with the mathematical prior distribution in our head. We really have to think hard about this in order to get something to plug into these equations. So how do you think about the prior? The first step is to understand that in the Bayesian context, the prior and the likelihood together jointly form a model of your uncertainty about the problem. We have a lot of experience with models in the sciences. What do we do with models? Well, we apply them to problems, see what they say, try alternatives, try to break them, try to think about what their assumptions are. This is something we do all the time, whether we're a statistician, an epidemiologist, a physicist, an economist, everywhere. So it's no different for a prior. Prior is part of a model, but it's a model of this weird sort of abstract thing, uncertainty, and not reality. So it's a little more difficult to think about. So let me help you think about it. There are a couple of tricks you can use, and the big ones are really crucial. First is to focus on the distribution of observables. Think about the data, basically. It's a lot easier to have strong, valuable intuition about what the data should look like than it is parameters. And then you can convert that intuition into intuition about parameters. But that conversion is less than straightforward. So how do you do that? Well, transform the model. Transform everything you can in the model to make it easier to think about. Transform data, transform parameters, transform covariates, everything. Now, we'll get into an example where we show very concretely how to make these transformations, but it really depends on the model, so it's hard to give general rules. But once you have these transformations, well, it's time to pick a prior. What do you do? What I'm going to say is you start with a reasonable default prior. What do I mean by default? Well, something that's weakly informative, so spread out but not too much, questions that you care about. And that last part is key. You can't have something that's weakly informative or uninformative for literally everything. That's impossible. You can be weakly informative for the question you're asking. What's the likely value of this parameter? What's the forecast that I'm interested in? That sort of thing. So spread out, but not too much. Let's operationalize that. And you know what? Let's just operationalize the whole prior. So let's just use a normal distribution as our default prior for any parameter. We're going to choose the mean and standard deviation of that normal distribution judiciously in order to make it work. So the mean should be the value you expect, or whatever you would set as the null hypothesis for that parameter, depending on your inferential goals. For a forecast, you might just use the value you expect. If you're trying to learn about that parameter, you might use the null hypothesis method because you want to sort of ape a hypothesis test. The standard deviation you should set so that the mean plus or minus the standard deviation is the most extreme value you think is realistically possible for that parameter. And what this implies is that there's a 32% chance in the prior that the parameter will be more extreme than you think is possible. So it allows for crazy values to happen, but it does lightly constrain them. It does say, maybe not too much. So that's what I mean by spread out, but not too much. It allows insane things to happen, insane according to your expectations, but not a lot. So let's apply this to an example. So I have a hypothetical example here. We have a network of 100 car dealerships. They're selling 4x4 pickup trucks. I cannot tell you what type of pickup truck they are selling, but I can say that the company or organization which manufactures these pickup trucks, they do use SAS somewhere. So in any case, this network, they're looking to expand. They can construct a new dealership in a bunch of different potential locations. And they want to predict that dealership's sales using price, some climate variables, some demographic variables. You can see them here. So what are they going to do? They're going to fit a regression model. And they're really interested in price because that's the variable they can control. They can't control the weather yet, unfortunately. So let's think about priors for a regression model in this context. We're going to start with default priors. We're going to start with the slope coefficients. So how do we handle these slope coefficients? Well, we need to make them easier to think about. We need to transform them. So first things first, if we have positive constrained covariates and a response is positive constrained, which it is because it's sales, we can take logs, and then the coefficient is an elasticity. So we can interpret that beta so that a 1% change in the original untransformed covariate is associated with a beta percent change in the original untransformed response, in this case sales. This is great because it's unitless. It's a lot easier to think about. So how do we choose the default prior for this parameter? Well, the null hypothesis is pretty easy, right? Slope coefficient, null hypothesis, no impact. What about the most extreme value possible? Well, you can argue with me on this one, but I'm going to say plus or minus 4. So that would say a 4% change in sales in response to a 1% change in the covariate. That would be pretty surprising in an economic context. Maybe not in a physics context. But for economics elasticities, I think this is reasonable. But if you want to disagree and go a little bigger, a little smaller, go for it. We plug those into the formula, get this prior, normal 0, 4 squared. And now I also want to emphasize these priors we're going to specify are independent of each other. So you can put dependent structure in your prior if you would like. However, that's not really where you want to start for a default prior. It's a lot harder to think about and beyond the scope of this talk. Now, what about covariates which are constrained, or not constrained, sorry. So you can't take a log of a negative value. So how do you think about these covariates and the associated coefficients? Well, we can standardize them. Subtract the sample mean, divide by the sample standard deviation, and then think in terms of standard deviation unit changes in the covariate and the response. So these are a lot easier to think about. And so let's use that. So what's the null hypothesis for this sort of coefficient? Again, 0. We expect no impact. The most extreme possible value? Well, I'm going to use the sample standard deviation of the response to frame my thought here and say a 4 standard deviation change in log sales in response to a 1 standard deviation change in the covariate in question would be pretty surprising. Anything beyond that is probably impossible, which again, the prior, which you see here, will allow this impossible thing to happen about 32% of the time. Now, some people start getting nervous whenever you start using data in order to choose your prior. And it's true that if you look at the equations, pure as the golden snow, in the Bayesian context, the data does not and should not impact the prior. Unfortunately, we are humans. We don't know our prior, and using data to help construct our prior is really, really useful because it's a very difficult problem to operationalize that prior. So I think it's fine to do that, but you do have to be careful. So anyway, we've done our continuous covariates. What about a class variable, categorical variable covariate? So we have all these dummies, right? So the basic method here is to think about an intuitive base case, a base group, and say what happens when we move to a different group. And really this idea generalizes to more complicated models where it's harder to apply the other tricks. Start with a base case and deviate from that base case and think about how that impacts the response. Nonlinear models where the impact of the covariate depends on the other covariates. This is very useful. So in this case, for just a categorical variable in a linear regression model, a change from the base group to a different group is associated with a beta change in the log sales response variable. That's how we interpret it. So how do we choose a prior for that beta? Good default is to say, well, expect it to be about the same as a one standard deviation change in a continuous covariate. So we'll use the same default prior, independent of each other, of course. Now, you might disagree with this. Maybe group membership for your group variable is way more important for your problem. Okay, fine, choose a different prior there. Maybe it's way less important, same idea. But this gives you this sort of way to think about the problem, right? You start with the continuous covariate and use that to frame your thoughts on the categorical covariate. Now we have one more regression coefficient, and that's the intercept. That's a lot harder to think about because, well, there's this quagmire of interpretation depending on how you transform things, what the values of all the other parameters are. So to sort of cut the Gordian knot and make this easy, I'm going to do something sort of like an empirical Bayes type idea, if you're familiar with that. But the basic idea here is to center the prior on the OLS estimate of the intercept, and then set that prior standard deviation very large so that it doesn't really have much impact for that parameter. Now, if you cared a lot about this parameter for some inferential question you have, you'd want to do something a little more principled. But as a nuisance parameter, this is fine. And so prior I choose is centered on 8.88, because that's the OLS estimate, it turns out, of that intercept. And this prior standard deviation is 100, which is about 2 orders of magnitude larger than 4, the largest prior slope standard deviation. Finally, you have the error standard deviation, the last parameter of the model to choose a prior for. And I want to emphasize error standard deviation and not variance. Variances are bad. They're very difficult to think about because their units are squared. Standard deviations units are the same as the response. Much, much easier to think about. There are also some problems with commonly used variance priors having pathological problems, but that's less of an issue because you can just use different priors. So think in terms of the standard deviation. How do we apply the default prior to a standard deviation? The standard deviation is constrained, can't be negative. Well, constrain the prior, make it a positive truncated normal distribution. And to pick M and S, M equals 0 is a good default choice. You can choose something else if you want to kind of center that prior a little bit. And then for S, if you set that to the sample standard deviation of the response, that's really the most extreme value that's possible. If you remember partitioning sums of squares in the OLS estimate, it's always bounded from above by that sample standard deviation of the response. This isn't true in the Bayesian context because you can have arbitrarily weird priors making that thing do all sorts of weird stuff, but it does require arbitrarily weird priors, and we're trying not to do something arbitrarily weird. We're trying to do something that's a good default prior. So it's a good upper bound that we think is constraining this parameter. And then, of course, we don't actually constrain the parameter. We give it a 32% chance of going above that bound using our default prior. So that's a default prior. We can go ahead and fit that model, get results, interpret them, start running with things, right? That's great. But we were interested in price, and we want to move beyond the default prior. So let's talk about informative priors and focus on this price coefficient. Do we think that coefficient can be positive? No, probably not. As Vizzini would say, redacted Vizzini from The Princess Bride, it's inconceivable. So if you haven't seen this movie, please do yourself a favor. Go watch The Princess Bride tonight. Something to do during quarantine. Classic. Vizzini, if you have seen it, says that this is inconceivable, cannot happen. So what do we do with inconceivable things in the prior? We force them to never happen. So we can use a negative truncated normal distribution as the prior for that beta. And then the posterior will never be negative. That's great. We can do that. But maybe it's not a good idea. Vizzini's partner in crime, Inigo Montoya, would say, yeah, that's not really what the word inconceivable means. Really, we think it's unlikely. So how could increasing the price of the truck cause more sales of the truck? That's really the question here. And there's this theoretical curiosity, mostly from economics, called a Giffen good. Probably not a truck. This is a very weird situation for that to happen. But there are other possibilities. Maybe consumers are using the price of the truck as a signal of quality. Or they're using the price to signal to each other. The more expensive the truck, the more rich they are. That gives them social status. These are possibilities. Maybe these effects aren't large enough to make increasing the price increase sales, but it could happen. So you want to allow for the possibility in the prior, if not letting it be a very likely possibility. So better choices for these priors I have listed here, and these are based on some outside empirical studies of the price elasticity of demand for pickup trucks, and you get estimates that go from about -1 to -2, depending on your estimation method. And the standard deviation of these priors is chosen so that really a positive price elasticity of demand is extremely unlikely, but it could happen. If the data screams at you that this is happening, okay, fine. We're going to allow for it in the posterior. So we chose some priors. We went through some examples. I want to sort of summarize the basic ideas here outside of the examples. The main ideas for how to think about the prior are to focus on the distribution of observables, because data is easier to think about than parameters, and then use transformations to help translate these intuitions about data into intuitions about parameters. Transform everything. Transform everything you can. Now, I want to emphasize these are tricks, not theorems. So, if they don't seem to apply for your case, don't use them. Maybe use them as an inspiration to come up with tricks to help you think about your problem, but don't think that they must apply. We came up with this default prior for any parameter, normal distribution with the mean and the standard deviation chosen in this particular way. But I want to emphasize that you should try alternative priors, try informative priors, try alternative means of specifying the default prior. Because, well, if the prior has a large impact in your results, well, you want to know that. You want to know what the crucial points of your analysis are. So I also want to take a minute to show how you would fit this model in PROC QLIM. So PROC QLIM is an econometrics procedure that does quantitative limited dependent variable modeling, but part of that it does linear regression. You could specify that like this. You can see my mouse right here. So you just basically have this base statement and these prior statements to control the prior distributions. And this prior on the standard deviation parameter is automatically truncated. But I mainly want to show this because I want to show you a teaser of what's coming up. So PROC QLIM, which is a CAS-enabled version of QLIM, currently exists but does not have Bayesian features in it. Well, those are coming soon. They are in the works. And you can see what that syntax may look like. Look, you can specify that normal prior in terms of the standard deviation if you would like, or the variance. And you can also explicitly specify the lower and upper bounds for truncated priors for any parameter, which is useful, and a little bit different syntax elsewhere. And because it's CAS-enabled, you can call the CAS action that underlies this QLIM action from any client, not just SAS. For example, here's how you would call it in Python. You could also call it in R or whatever. So if you're interested in that, well, make sure you pay attention to the upcoming releases. With that, I'll stop and thank you for your time. If you have any questions, please do not hesitate to shoot me an email.